Welcome back. I'm Muggsy, and today I'm going to explain the periodic table of the elements. In the 19th century, scientists had a pretty good idea of a lot of information about the elements. They were starting to understand the structure of the atom. But the periodic table as we know it now didn't exist. They just basically knew how big the elements were. And so in 1869, a Russian scientist named Dmitri Mendeleev was looking at all the elements as a big long list, and he had them arranged by atomic mass. So the smallest element, hydrogen, would be first, and then the next lightest element, helium, etc., moving them forward. Now, mass didn't end up being the best way to organize the elements because isotopes exist, and so eventually scientists would hit on organizing the elements by number instead of mass, because if you organize them by number, it's the number of protons in the nucleus, and that doesn't change. Isotopes don't affect the number of protons in the nucleus. So what I have up here is a list of some of the earliest elements, I think maybe the 36 first elements, organized by atomic number, starting at number 1, hydrogen, then number 2, helium, etc. And we wrote them out just as Dmitri Mendeleev would have written them out, as a big long list. But I've kind of run out of space in my board when I got to argon, so I repeated another line. So from argon I went to potassium, and then forward from there all the way to krypton. Repeats are known as periods. And periodicity is just the process of repeating over and over again. If you receive a periodical, such as a newspaper or a magazine, I know these are pretty old and outdated, they repeat. You might get your newspaper every day. You might get a magazine once a month or once a quarter or once a year. Even a period, as women experience, it happens repeatedly, once a month, over and over again. And so we added a repeat known as a period. Okay. When I did this repeat, I noticed that my hydrogen and potassium kind of lined up in terms of their ionic charge. Hydrogen forms an ion with a charge of +1, and so does potassium. They both form cations. So Mendeleev came up with the idea of seeing if we can repeat this table in a way so that the ionic charges of the elements and the number of bonds they form line up. So let's see if that's possible. Let's start with hydrogen, which has a charge of +1. Then we have helium, which, as you know, is a noble gas, doesn't form any ions at all. Won't form a cation, won't form an anion. Okay, well that's no good. Then we get to lithium, which also has a charge of +1. So let's add a repeat, let's add a period. And in fact, we could call this first line period 1, and we could call this second line period 2. So now we've got lithium, then we've got beryllium, which has a charge of +2. Okay, well that doesn't really line up with helium, that's no good, but I'll just put it here anyway. Then we've got boron, which really doesn't form an ion at all, but it does form 5 bonds, which is kind of like having a charge of 3+. Then carbon, which again doesn't form an ion at all because it can form 4 bonds. So it really doesn't want to lose 4 electrons or gain 4 electrons. So I'm not going to put any charge at all there. I'm just going to say it forms 4 bonds. Then we've got nitrogen, which forms an anion with a charge of -3. Oxygen, anion, charge -2. Fluorine, anion with a charge of -1. And then neon, which doesn't form any bonds at all. It's totally stable all by itself. Now you'll notice I've got neon here, I've got helium here. Now helium doesn't really line up with beryllium. So what if I erase helium from its current position and move it all the way over here on top of that neon? And now everything lines up actually. So I've got my +1 charges, I've got my no bonds over here. We've made it all the way here to neon. let's keep going. My next one is sodium, which has a charge of +1. So that's going to line up here in the +1 column. And let's call that period 3. Then I've got magnesium, 2+. All right, nice. That lines up perfectly with beryllium. Aluminum, 3+, looking good. Lines up with boron. Silicon forms 4 bonds but doesn't form any sort of ion. Perfect. Phosphorus, 3-, excellent. Lines up with nitrogen. Sulfur lines up with oxygen with a -2 charge. Chlorine and fluorine both have -1 charges. And argon also has a charge of 0. It doesn't form any anions or cations. It's totally stable all by itself because it has 8 out of 8 valence electrons. Okay, so we formed another row and everything's seeming to line up. So when Mendeleev got to this point, he must have realized that he was onto something. He was creating a new way of structuring the elements so that they line up in these neat columns. Every column has similar chemical properties, right? So this column here, column 1, all of these form cations with a charge of +1. And this column here, we could call that 1, 2, 3, 4, 5, 6, 7. All of these have form anions that have a charge of -1. Column 8, well, they don't form any cations or anions. They're totally stable all by themselves. Wow, so he's creating kind of a table structure for all the elements. And of course, you know this as the periodic table. But let's keep fleshing it out a little bit. Let's keep adding elements to our list and seeing if this table structure works for all of them. So now we've gotten to argon, we're over here. We go back to potassium, which has a charge of -1. And we're down here, we'll call this our 4th period. I'm not gonna write out period anymore, I'll just put a 4 there. And I guess we could number our columns. Now, he noticed that all of these columns have similar chemical properties, so he decided not to call these columns anymore, he calls them groups. Whereas the rows, as we discussed earlier, are called periods. Now, elements in the same period don't really have anything in common. All they have is that they're basically aligned by atomic number. So lithium has atomic number 3, then beryllium's 4, boron's 5, carbon 6, etc., etc. But they actually are very different, right? Lithium forms a cation with a charge of +1. Nitrogen forms an anion with a charge of -3. Neon doesn't form any kind of ions. So elements in the same period don't really have anything in common. Elements in the same group have a lot in common. That's why he uses that term group, because things within, people or things within a group tend to be similar, right? That's the point of a group. Okay, let's keep moving. So potassium, as I said earlier, has a charge of +1. Calcium, +2, perfect. Oh, interesting. Okay, now that I'm down to scandium, scandium actually doesn't form a reliable charge like 1 or 2. It can be different things at different times. And in fact, that's true of all of these elements here, all the way through zinc. They can be different. For instance, iron sometimes has a charge of +2, sometimes it has a charge of +3. So all of these elements don't work easily into this table that I've created. But if I skip them, I can see that gallium has a charge of 3+. Okay, so if I skip all those guys, I guess I could put gallium right here. And then arsenic has a charge of 3-. So that would go right, whoa. No, there's a problem. I can't put arsenic right here because arsenic has a charge of 3-, and this column is all elements that don't have a charge of 3- when they form ions. They tend not to form ions at all. They form 4 bonds, such as carbon and silicon. So arsenic really should go here with the other 3 minuses. And then selenium, which also has a charge of -2, should go under oxygen. And then bromine, which has a charge of -1, should go with fluorine and chlorine. And then krypton, which has no ionic charge at all, which is stable all by itself, should go with all these other guys here. So that's weird. So between gallium and arsenic, it looks like there's a missing element. There should be something there that forms 4 bonds. And Mendeleev thought that everything aligned so perfectly in his table that surely there should be something here. There should be an element that has an atomic mass bigger than gallium but less than arsenic, and that also forms 4 bonds. But no such element existed. So he called that ecosilicon, which just means under silicon or next to silicon, because there should be some kind of element right here under silicon. Now again, he made this table in 1869, so he just left this gap. And people said, well, that's weird, there's a gap there, maybe this table isn't any good. Well, about 15 years later, in 1886, is that 15 years? Almost 20 years, I guess. They discovered an element known as germanium, which I guess you could probably guess where they discovered it, in Germany. And germanium has an atomic number of 32, gallium has a number of 31, arsenic has a number of 33, so it's the missing atomic number, and germanium forms 4 bonds. So Mendeleev's periodic table was so correct and so powerfully predictive that he left a spot for an element that would later be discovered almost 20 years later, and that element was germanium. So the periodic table is a man-made way of representing the patterns that the elements experience in nature. And it's a very useful tool. You're going to be using it throughout your chemistry course. But there are some issues here. For instance, we left out all these elements here that have transitional ionic charges. Sometimes they're one thing, sometimes they're another. Those are called the transition metals. And then Mendeleev would actually alter his table to make a spot for all the transition metals between columns 2 and 3. So right here, he would stick all these elements, which would spread the table out and create the periodic table as you see it today. Same thing with the lanthanides and actinides down below. Those are kind of inserted into the table because otherwise the structure of the table wouldn't make as much sense. Okay, so let's just review the periodic table. It's organized by increasing atomic number. Hydrogen is in atomic number 1, and then it goes from left to right. Helium is 2, lithium is 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. Repeating, increasing atomic number. Every time the table repeats, that's called a period. That's why it's called the periodic table. And then because of these periods, because of these repeats, it makes it so similar elements line up in a column, and these columns are known as groups. The groups tend to have different names. Some of them I don't make my students memorize, such as the pnictogens and the chalcogens. Other ones I do. So let me just briefly show you the groups that I expect my students to memorize. This first group here, with the exception of hydrogen, are called the alkali metals. Alkali metals are all highly reactive because they just need to lose 1 electron to become stable. They tend to be metals. We'll talk about states of matter in a moment. And they tend to form cations with a charge of +1. Likewise, right next to them, in group number 2, we call these the alkaline earth metals, which sounds really similar to alkali metals because they are. They're also metals, and they also are fairly reactive, not quite as reactive as the alkali metals, but still very reactive, and they form cations with a charge of +2, because if they lose 2 valence electrons, they become stable. The other two that I ask my students to memorize, over here in column 18, now you might say that looks like an 8, not an 18. Yeah, it is an 8, but we're forgetting about all these transition metals that are going to move it over. So this is column 18, but you can also know it as column 8A. And elements in this column tend to have 8 out of 8 valence electrons, with the exception of helium, which has 2 out of 2. We call them the noble gases because the octet rule is satisfied and they're totally stable just the way they are. They don't form anions, they don't form cations. They don't really bond with anything. There are a few exceptions to that, but for the most part, you can find them in nature in their pure unbonded state, which isn't true of most other elements. Next to them, in column 17, or 7A, these are known as the halogens. And the halogens, fluorine, chlorine, bromine, iodine, etc., are very reactive elements, usually gases, and they are extremely reactive. They're nonmetals, and the reason they're so reactive is they have 7 out of 8 valence electrons in their ground state, so they only need to gain 1 electron to become stable, so they'll readily form bonds with anything they can, either covalent bonds with other nonmetals or ionic bonds with metals by taking electrons from those metals that want to give them up. Okay, so the alkali metals in column 1, alkaline earth metals in column 2, halogens in 17, and the noble gases in 18. Those are the only 4 groups that I usually ask my students to memorize. Okay, a few other things about the structure of the table. I'm looking at my periodic table here at learnsomething.app, and you can see that the elements can be separated into 3 basic categories. The metals, which are the majority of the elements in the bottom of the periodic table and also the left-hand side of the periodic table, with the exception of hydrogen. The nonmetals, which are over on the upper right-hand side of the periodic table, and then of course also including hydrogen. And then the metalloids, which exist in this kind of diagonal between the metals and the nonmetals. You can see a few of these elements. They're not listed as metal, nonmetal, or metalloid because these really big elements at the bottom of the periodic table have only been created in particle accelerators. They've only existed for brief nanoseconds, not long enough for scientists to really know what they look like or what they act like. It's not like we can get a whole bar of elements 117 and 118 here, right? We just get microscopic particles. Metals are exactly as you kind of know a metal to be. They tend to be shiny, they tend to be hard, they're solid at room temperature with a few exceptions like mercury. If you were to pound on them, you could flatten them, that means they're malleable, and you could draw them into a wire, that means they're ductile. Nonmetals are basically the opposite of that. They tend to be gases at room temperature, not solid. If they are solid, they're not shiny, they tend to be dull, and they're not malleable or ductile, they tend to be brittle. Metalloids are really interesting in that sometimes they behave like metals and sometimes they behave like nonmetals. So sometimes they might be electrically conductive, other times they're not, and that's what makes elements like silicon so cool, in that if you can be conductive some of the time but not all of the time, you can create a variable signal that basically is the basis of binary computer code and all of our computer technology. That's why computer chips are made of silicon, for example. So yeah, all of the elements can be separated into those 3 basic categories. Blocks are another really useful way to look at the periodic table. And you can see that we've got 4 basic blocks. The S block in orange over here, the P block in blue over on the right-hand side, the D block in the middle, and the F block at the bottom. And now, if you've already done electron configurations, you'll recognize these blocks from doing electron configurations. For instance, if we wanted to do the configuration of carbon, we would say that's 1s2, 2s2, 2p2, right? Because we have 2 electrons in the S block, hydrogen, helium, then 2 more in the second S block, lithium and beryllium, and then we go to the first P block, which starts at 2, 1, 2. Okay, you don't need to know that for this periodic table unit, but If you've done electron configurations, or if you're going to do electron configurations, these blocks can be really useful. An important thing about this kind of block model is it separates the elements out into basically three main groups. The D block is basically all of the transition metals. So in green here, these are all of our transition metals like iron and copper and gold. The F block are our inner transition metals, also known as our lanthanides, named after lanthanum, and actinides, made out of actinium. And they're kind of inserted in this little space here. So you'll notice lanthanum is element number 57, and then we go to 58, 59, all the way to 71, and then we go back to hafnium here. So they're kind of like these bottom two rows exist in this little space right here between 57 and 72. The reason we don't put them there is that if we did, it would stretch out the periodic table, and then we wouldn't be able to see these trends the way we can, the way it is now. And then, so we have our inner transition metals in pink, our transition metals in green, and then we combine the the S and P blocks into what we call the main group elements, or the representative elements. And the representative elements, like lithium, beryllium, carbon, fluorine, are really common in nature. If you think of living things, we're mostly carbon, hydrogen, oxygen, nitrogen. All of those are representative elements, right? So representative elements are really common in nature, in the world around us, in our atmosphere, in our oceans. And representative elements are really cool in that they're pretty simple to work with from a chemistry standpoint, in the sense that everything in column 1A has one valence electron. Everything in column 2A has two valence electrons. Everything in 13 or 3A has 3, 4, 5, 6, 7, and everything in 18 or 8A, the noble gases, has 8 valence electrons. That same pattern does not work for the transition metals. Good guess how many valence electrons they have. And same thing with the inner transition metals. So these representative elements, also known as main group elements, the ones found in the S block and P block of the periodic table, are again really common and really easy to work with from a chemistry standpoint. Okay, so we've gone over metals, nonmetals, and metalloids, and we've gone over blocks. I'd say we could talk about phase. You can see most of the elements at standard temperature and pressure are solid. There's just a few that are liquids, mercury, bromine, and copper, nicium. And then quite a few that are gases, and then these tend to be our nonmetals: hydrogen, helium, fluorine, chlorine, etc. Of course, there are some nonmetals such as carbon, phosphorus, and sulfur that are solids at room temperature, but many of the nonmetals tend to be gases. The only thing I would like to show you here is maybe groups. Again, we have our main groups that we tend to ask students to memorize here. The alkali metals are in this first column, and note that the alkali metals in light blue don't include hydrogen. Everything in that first column has one valence electron, so that's why hydrogen's in that column. But it doesn't make sense to include hydrogen in the alkali metal group because it's not a metal, it's a nonmetal, right? So all these alkali metals have a lot in common, except for hydrogen, since it's a nonmetal. Hydrogen maybe in some ways should be over next to helium in column 17, but the reason we put it in column 1 is it has one valence electron. It doesn't fit perfectly in either spot. It's kind of a wild card. In column 2, we have the alkaline earth metals. Again, these are very reactive, but not as reactive as the alkali metals, and they tend to form cations with a charge of +2. 15 and 16, these columns are the pnictogens and the chalcogens. I tend to not ask my students to memorize these. I don't have them memorized myself. I just think of them as the nitrogen group and the oxygen group. And then column 17 is the halogens, and column 18 is the noble gases. So the periodic table is just a device that helps us organize and understand the elements, just like Roy G. Biv is a device that helps you memorize the colors of the rainbow, or King Philip plays chess on fine glass sand is a way of memorizing the kingdom model of biological classification. It was created in the 19th century by Dmitri Mendeleev, and we still use it today. It's still a very powerful and useful tool for organizing and understanding the elements. It consists of periods, or the horizontal rows, and groups, which are the vertical columns. Elements in a group have similar chemical properties, but elements in a period don't. They're just basically increasing in atomic number, 1, 2, 3, 4, 5, etc. The metals tend to exist on the left side of the periodic table and also the bottom of the periodic table, with the exception of hydrogen, which is on the left but is a nonmetal. The nonmetals are on the upper right of the periodic table, and the metalloids are right between. The four groups that I ask my students to memorize are the alkali metals in column 1, the alkaline earth metals in column 2, both of which are metals and are highly reactive, forming cations with a charge of +1 and +2 respectively. I also ask my students to memorize the halogens in column 17, highly reactive nonmetals that really want to gain 1 electron to become stable. And the noble gases in column 18, which are already stable and won't form bonds with other things. I hope this helps you understand the periodic table. I'll see you next time.